Right, we're at the top of the hour, so let's go ahead and get started. Hi, everyone. My name is Julia Matevosyan. I'm an Associate Director and Chief Engineer with Energy Systems Integration Group, or ESIG. ESIG serves on a leadership team with Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors across the globe to catalyze rapid clean energy transition at an unprecedented scale and speed. This is being done by providing coordinated and holistic approach to necessary knowledge, education, and support to power systems across 5 action pillars. At the core of the G-PST is a large cross-section of power system operators from around the world who are dealing with rapid transition from a system based on synchronous machines to one based around inverter-based resources. The 5 pillars of the consortiums include research and peer learning, technical support, workforce development, standardization, and open data and tools. For more information on G-PST, you can go to www.globalpst.org. We would like to welcome you to this webinar in our joint G-PST Pillar 1 ESIG webinar series. This series is in addition to regular ESIG monthly webinars and focuses on G-PST research agenda associated topics being addressed in Pillar 1. These topics are presented both by system operators as well as members of industry and research community. An additional series of webinars on other 4 pillars of G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to www.globalpst.org and click on Get Involved tab. Further information on ESIG can be found at www.esig.energy. Next, I would like to go over a few logistical matters. First of all, the lines will be muted for the duration of the webinar to avoid unnecessary distraction. For Q&A, as always, use Slido platform at slido.com. To ask your questions, please navigate to slido.com and enter ESIG 11 as an event code. The instructions are also at the bottom of the screen right now. You'll see thumbs up button next to questions in Slido, and this allows you to cast your vote and help us prioritize the questions submitted. We plan to save 10 to 15 minutes for the Q&A at the end and wrap up at the top of the hour. An email with a link will be provided once the video file has been posted, and we also plan to provide short responses to all unanswered questions after the webinar. So please don't be afraid to ask your questions through Slido. So just a few words on the topic of today's webinar. Grid-forming resources are poised to play a key role in maintaining reliability and stability of modern power systems with high levels of inverter-based resources and large electronic loads. Proactive development of grid-forming technologies can help mitigate reliability challenges that would otherwise require extensive transmission investments. To support the adoption, well-defined test methods and performance metrics are needed to evaluate and specify grid-forming behavior. This webinar will present the findings from newly released ESIG report on testing the voltage source behavior of grid-forming resources, which provides comprehensive guidance for assessing the voltage source behavior of both inverter-based and rotating machine-based resources. The webinar will provide attendees with a clear understanding of how standardized testing performance metrics can accelerate the reliable integration of grid-forming technologies into future power systems. The speakers today are Shakil Shah, and he's a principal engineer in the Power Systems Engineering Center at National Renewable Energy Lab, or NREL, in Golden, Colorado. His research focuses on stability of power systems with high levels of inverter-based resources and large electronic loads, with specific emphasis on impedance-based frequency scan methods for stability analysis and performance characterization of power electronic devices. He holds PhD in electrical engineering from Rensselaer Polytechnic Institute in Troy, New York, awarded in 2018. The second speaker is Deepak Ramasubramanian. He is principal technical leader at Electric Power Research Institute in the Transmission Operations and Planning Group. Deepak works on modeling, control, and stability analysis of bulk power systems with specific focus on impacts of large-scale integration of inverter interface generation and loads. He received his PhD degree in electrical engineering from Arizona State University in 2017, and his master's in technology degree in power systems from the Indian Institute of Technology in 2013. And without any further ado, let's go ahead and get started. Please remember to use Slido to put your questions and cast your vote for your favorite question. And with that, let's go ahead. Shahil, I turn it over to you.
Yeah, thank you, Julia, for introducing the topic and me and Deepak. Let me share my screen. So can you confirm that you're able to hear me okay and see my slides? Okay, great.
Good.
Yeah, thanks. So Julia has already introduced the topic, so I'll skip this one. So me and Deepak, we are going to talk about this ESIG report that we have been working for last couple of years, and it was released in September 2025. This report focuses on testing the performance of grid-forming resources, providing test methods and performance metrics, particularly for voltage source behavior. We started as a more like a technical paper, and then with some broader view about covering different test methods. But then we realized that there's a lot of material out there on a variety of different topics of testing grid-forming resources, but very limited information on how do you quantify the voltage source behavior, which is actually, if not the core, one of the core requirements for grid-forming resources. We covered in this report, we are covering pass-fail criteria based on frequency scans or frequency domain analysis, uh, time domain tests, including phase jump and voltage jump, and frequency domain tests, including impedance scan or V by I scan, Q by V scan, basically the what I call reactive power scan, and then P by theta scan or active power scan. Here's the link for the report if you want to access. I think Lacey will also put that in the chat box. So before we go into the contents of report and give overview of this report, I would like to acknowledge contributions from many different folks to this report. On the screen, you see, along with me and Deepak, the folks who have contributed to this report. In addition to the technical material that we've received from different contributors, there was a lot of editing in terms of the language to avoid confusion, be very precise and concise on what we mean by different tests and different performance metrics. So the outcome is, I'm very happy with that. Like, it is very crisp and to the point in terms of voltage source behavior, which is one of the key characteristics for quantifying grid strength and providing stability to bulk power systems. At this stage, I would also like to acknowledge our funding agencies, like particularly for NREL's team. The contribution was supported by DOE office. Jianfu from DOE supported this activity, and from APRI side for Deepak, it was a Unify Consortium. So let's start with tests for quantifying the voltage source behavior. And basically the fundamental premise for that. And the question is like, okay, why do we want to test grid forming resources for voltage source behavior? And then what should be the framework for doing that? The framework we have chosen is a voltage source behind reactor. And that is we want to use that as our platform for comparing the voltage source behavior of any grid forming resource with this very simple setup. And there are two reasons for that. One is most synchronous machines, or I should say all synchronous machines within a particular frequency range, they behave like a voltage source behind reactor. As we power system engineers, we routinely represent synchronous machines by this behavior. The second reason is that when we test inverter-based resources and now large electronic loads for the performance, we usually test them in single machine infinite bus setup where we connect them, or basically we represent grid by this very simplistic or very simple topology, which is voltage source behind reactor, and we see that under what grid strength conditions that device is remaining stable. So that is the second reason why we want to use this as a framework for quantifying the voltage source behavior. Now, there are two ways to do that. One is the time domain approach, where we can quantify the behavior of a resource uh, to act as a voltage source behind reactor. And the second approach is in the frequency domain. So here I'm showing basically the reactive power response in the time domain for this voltage source behind reactor. So right now we are still talking about all these responses that you see on the screen. They are for this voltage source behind reactor. So it's not any inverter, it's not any generic model or any experimental result. And as we see, like in this response, whenever there is a drop in the voltage at the POI, this voltage source behind reactor will immediately dispatch some reactive power to basically stabilize the voltage at the point of interconnection. The amount of response is going to be inversely proportional to the magnitude of impedance of the reactor. So if the reactor impedance is large, the amount of response that you will receive from uh, this voltage source behind reactor would be smaller. The second thing is, depending on what is the resistance of the reactor, the response can be oscillatory or it will be damped. So that is looking at the voltage source behavior within the time domain. We can look at the same behavior in the frequency domain on the right. And if we derive the transfer function of from voltage magnitude at the POI to the reactive power output from voltage source behind reactor, that is transfer function from V to Q, it turns out to be a low pass filter, second order low pass filter, with corner frequency being same as around the fundamental frequency, 50 or 60 hertz. And the gain is below the fundamental frequency, the gain is pretty much flat or constant, and the phase is 180 degrees. And this intuitively makes sense because what we are seeing is that the voltage source behind reactor will act as a negative DC gain in subsynchronous frequency range in transfer function from V to Q. The reason it makes sense is that because the negative gain shows that if the voltage goes down, the reactive power output of the voltage source behind reactor will go up. The another part is that this behavior in a way translate the time domain into the frequency domain, and whatever you see within time domain, which is basically cramped within like a very small window, within the frequency domain, it is broadened over a broad frequency range, and this gives us ability to define the specifications within that frequency range or select that window. Another key highlight is that if you select a voltage source behind reactor, for example, this particular one, and size the reactor to provide a particular short circuit ratio. For example, here it is 2.5 for the base voltage of 0.69 kV and base power of 1 megawatt. When you do that, and if we plot this Q by V transfer function within per unit by per unit basis, this DC gain will be exactly same as the as a short circuit ratio of 2.5. So again, this gives you a direct connection of how much grid strength this voltage source behind reactor is giving you. Now, if you connect this voltage source behind reactor at any POI within the grid, you would know how much short circuit ratio it is providing. Now, can we take this understanding or the fundamental framework to grid forming resources? So does it work basically, does it work for real grid forming products or not? So here are a few experimental results. In the next slide, I'll show some scans from black box vendor models for grid forming resources. But in this experimental results, we are seeing a Q by V scan of 2.5 MVA synchronous condenser, a 2.2 MVA grid forming or grid following BESS inverter, basically the same inverter which can operate in grid forming or grid following mode, a 2.5 MVA type 3 wind turbine, and then a 2 MVA PV inverter. These are all experimental results. And the solid lines here show response of these devices when they are operating in grid forming mode. or with grid forming controls, I should say. And the dashed lines are response when the grid forming control is not activated. And clearly we see that the gain within this subsynchronous frequency range has that behavior of voltage source behind reactor, more so for synchronous condenser. Synchronous condenser, you really see this low pass second order filter with very low damping at fundamental frequency and then gain rolling off. And then phase also stays around 180 degrees. So the commercial products, they do satisfy this behavior for grid forming resources. Here is what I talked about in the previous slide was just a single unit, either inverter or wind turbine or synchronous condenser. Here you are seeing the scan, Q by V scan of entire plant obtained from vendor-specific black box PSCAD models or EMT models. The black trace over here represents a response of a synchronous condenser. And then the three other lines or colors, blue, purple, and red, they're all grid forming BESS from three different vendors. The response of this Q by V transfer function is plotted in per unit by per unit basis. So here to give like apple to apple comparison. And as you can see, all of these resources have that more or less constant gain within this 4 to 40 hertz frequency range, which is where we have selected to check the grid forming behavior. Because in steady state, even grid following controls can provide you this voltage source behind reactor type of response. We really are interested when we talk about grid forming in this fast timescale behavior in transient to subtransient timescales. So that roughly translates to 4 to 40 hertz, basically from few tens of milliseconds to couple hundred of millisecond type of response. Before we dive into different performance metrics and test methods for voltage source behavior, the another thing I would like to point out is that if we compare this dynamic short circuit ratio that is provided by these different resources, the synchronous condenser is providing around 6.5, whereas the grid forming BESS is the gain ranges from 2.5 to 4.5. This is again, we have seen this behavior again and again, where grid forming BESS, it does provide a good amount of dynamic grid strength support using this gain from Q by V scans or P by theta scans, but it is usually lower than what a synchronous condenser of the same capacity would provide. Deepak, can you go through this slide on impact of PPC?
Yeah. So the idea here is also to showcase that if you are looking at this both from an inverter or elemental level perspective versus a plant level perspective, because there's a difference between looking at this at the POI bus versus looking at it at the inverter terminals, and the role of the PPC usually comes into play more in the slower behavior, the kind of closer to steady state kind of a response, because it's a much slower control. So one of the things that we're showing here is that irrespective of whether the PPC exists or not, we see the voltage source kind of property being coming out more in that 4 to 40 hertz range. So if you compare the green curve with the orange curve here, wherein you have the orange curve, it is an OEM black box model at the inverter level. The green curve is the OEM black box model with a plant controller added on top of it. And then both have a supposed GFM property with it. So you see that although the phase plot of all of those curves, except for the red curve, does show that form of a constant gain, because as Shahil mentioned, right, the non-GFM inverters can also provide a form of a droop response, a form of a voltage support closer to steady state. But the phase plot really shows that actually that closer to 180 degree value that we're looking for in the transfer function really comes across only when you look at it at the inverter level. And if you look at it at the complete plant level, the plant controller can actually filter that behavior out in the lower frequency range, which lends more support and credence to why we're looking at that 4 to 40 hertz range, that the plant controller is not dominant in that particular time frame. And that is the time frame in which the frequency range in which we want the grid forming property to be assessed. So that just provides a little bit more background into how the range of frequency can be determined in which we want to address this property, and then also showing that effects of plant controller and if you're doing it as a plant level versus an inverter level testing.
Yeah, thanks, Deepak. So that was about basically the rationale behind selecting voltage source behind reactor as our basically a benchmark, and then selection of the frequency range, frequency scan, time domain testing. Now we will get into more different test methods, which we have included in the report, along with performance metrics. So first set of tests are basically pass-fail criteria based on frequency scan. So we talked more about Q by V scans initially, and there are two other scans, P by theta and V by I. Some similar rationale or reasoning applies over those tests as well. So for the pass-fail criterion based on Q by V frequency scan, we want a source. A source is grid forming only if the Q by V frequency scan has almost constant magnitude and constant phase response within this frequency range of 4 to 40 hertz, as well as the phase response stays close to plus 180 degrees or minus 180 degrees, which are the same angles. Now, you might ask, like, what is almost constant and what does it mean by closer to 180 degrees? So in the report, we haven't defined any particular metric for this checking the constantness or the closeness of the phase response. The pass-fail criterion for grid forming resource based on P by theta scan is similar. It's just that you look at a different transfer function, but look at the similar behavior, that the magnitude within this frequency range 4 to 40 hertz is almost constant, and the phase is either plus 180 degrees or minus 180 degrees or closer to that particular value. The pass-fail criterion based on V by I frequency scan, that is slightly different. So in addition to active power response and reactive power response, the third way to check the voltage source behavior is look at the equivalent Thevenin impedance of a resource or of a grid forming resource. If that resource is indeed behaving like a voltage source behind a reactor or within a particular frequency range, in that frequency range, its equivalent Thevenin impedance would be that of a reactor because ideal voltage source has no impedance. So this pass-fail criteria is based on that the V by I frequency scan should resemble the response of that of an RL branch or a reactor within the frequency range of F1 plus or minus 40 hertz. So 4 to 40 hertz in P by theta or Q by V scan, that translates to around the fundamental frequency, like 60 plus 40 or 60 minus 40, except for a small band around the fundamental frequency. Moving on to the testing setup. So the test setup is quite simple. Basically, we connect the grid forming resource to an ideal voltage source with a reactor in between, the variable impedance in between, and that is how we test the grid forming resource or the test setup. The variable impedance here is to achieve particular grid strength for the test, and we'll talk about it in a minute, like why we might need to use different grid strength for testing a grid forming resource. This test setup can be used either in EMT or PDT models. PDT here means phasor domain transient, or it can also be done using actual hardware, actual wind turbine or inverter, or any other grid forming resource like even STATCOM. Deepak, you want to say anything on this slide on PDT?
Yeah. So the reason why we also mentioned PDT here, because it may come as a surprise that we're looking at frequency domain criteria and testing on phasor domain models. This, to a certain extent, I think also links back to the previous webinar that we had on generic models and so on. Use of this frequency domain criteria has actually been able to be very useful in trying to evaluate the applicability of phasor domain models. So we can actually use these kind of scans that we're talking about here and then compare them against the EMT model scan, compare them against field measurement scans, and get a level of understanding on how accurate is the phasor domain model in actually representing all of this behavior, and to what frequency, with what bandwidth is the phasor domain model going to be accurate. And that provides a practitioner with more information on when to use phasor domain tools versus for what kind of events they should not use phasor domain tools. It also provides the practitioner information on understanding how good is the phasor domain model, how robust is it, what kind of characteristics can it represent, or is the phasor domain model, even if it's black box, just done in a quick hash method. The final thing we've used this tremendously for is actually parameterization of generic models. So we can now use these phasor domain scans, frequency scans in phasor domain to actually compare against the EMT domain scans and actually parameterize generic models for more accuracy and more robustness so that one gets the best value out of any model that is being used.
Yeah, thanks, Deepak, for providing that context. So I'll now talk about time domain tests and performance metrics. I'll just go through just one of the time domain tests. We talked about voltage jump and phase jump, but here I'll just talk about a phase jump. So here is a response of a grid forming BESS to -10° phase jump. This test is performed using vendor supplied EMT model, the black box model. And we see the active power response, reactive power response, and the response in the output currents. The active power jumps during this negative phase jump. It increases by around 25 megawatts from the pre-disturbance level. And then after around 50 milliseconds or so, it comes back to a pre-disturbance level. This, on the left side, the response is done when there is no impedance between the grid forming resource and the ideal voltage source used for emulating that phase jump. That means the SCR is infinite. And on the right is when we insert this impedance between the ideal voltage source and grid forming resource to create a weak grid condition of SCR of 1.25. Here the response is smaller. It's similar but smaller. As you can see, the response jumps by around 15 megawatts compared to 25 in this previous case. And also response is more oscillatory. So this brings some certain questions like, how do we provide performance matrix for phase jump response? Should it be the initial response, which can be different depending on the grid strength? Should we talk about the shape of the response, like it is triangular or more squarish? Or how do we specify the damping? Or should be the grid conditions? So we try to answer all these questions, developing consensus, and came with this performance matrix. So the performance matrix for phase jump tests are basically that and these are the numbers in the bold are the example number or the example values, which can be changed depending on the system requirements. So the first performance matrix is phase jump active power. A grid forming resource should increase its active power output by at least 5% or 0.05 per unit when negative 10° phase jump is applied to its grid voltages. Also, this additional response should be sustained for at least 100 milliseconds after a disturbance within the first 200 milliseconds after the disturbance. So we don't want to say that, okay, it should be higher than this particular level for 100 milliseconds, but it's more like any 100 millisecond within that 200 millisecond to accommodate different shapes of the response. The second part is phase jump rise time, how fast the response should rise. So it should rise to this particular level within the 40 millisecond after disturbance. Third is phase jump active energy, which is basically the area within the active power response compared to pre-disturbance level within the first 200 milliseconds. So again, we are trying to accommodate different shapes and different types of characteristics. We are really looking for how much energy the grid forming resource is contributing to the system immediately after a phase jump event. And then last is the grid strength condition. So under what condition this phase jump should be performed. So with SCR of 3 and X by R ratio of 10. As I said, all the numbers in the bold, they are example values. A user can change these numbers depending on what are the system requirements. For example, if you are going to commission this grid forming resource in a even weaker grid conditions like SCR of 1.8, then you would probably use that condition for checking performance to phase jump response. Voltage jump response is similar. You apply voltage jump at the POI and then look at the reactive power response, and the performance metrics are similar. You can look at them in the report. So moving on to the frequency domain tests and performance matrix. So first is Q by V frequency scan. We talked about how Q by V frequency scan should have a more or less constant magnitude within this 4 to 40 hertz. The phase should be closer to 180 degrees. And this is a response. This particular response on the slide is again from one particular vendor supplied black box model of grid forming resource. It shows that the gain is around 1.7 megawatts per 1% change in the voltage. And this correlates very well to the response we see in the time domain. Like this gain has a direct correlation with the voltage jump response. So this particular grid forming BESS, it passes through the Q by V frequency scan criteria. I think there's a typo here. Oh, no, it's not actually. I misread it. The phase is closer to 180 degrees. The gain is more or less constant between 4 to 40 hertz. And the gain is 1.7 megawatts per 1% change in the voltage magnitude. Again, as I said, it matches with the 7 megawatt response for 5% voltage drop in the time domain response, which I didn't talk much about, but it's particularly on this slide. So what are the performance metrics for Q by V frequency scan? So first is the magnitude of Q by V frequency scan should be higher than 0.5 per unit by per unit. Again, this is an example number. What it really shows is that the dynamic short circuit ratio that I talked about is 0.5. Basically, 100 megawatt grid forming BESS would contribute grid strength of around 50 megawatt. In reality, as I showed in the previous example, the grid forming BESS, they provide this gain of around 2.5 to 4.5. So you can demand this gain to be higher. We are just keeping this performance matrix more relaxed in the report, so that if anyone is using this performance matrix as it is not too demanding for the technology. But ideally, you would like this to be at least more than 2 to 2.5. And then the phase response should be equal to plus or minus 180 degrees within this frequency range of 4 to 40 hertz. But we are giving the tolerance of 60 degrees. So there can be an error of 60 degrees compared to this. Again, we have kept this tolerance much wider. We would rather have it like 20 or 30 degrees. But if someone is using this matrix without doing any studies, without understanding its impact on the technology, for example, wind plant or PV plant might not be able to provide this response with such tight bands, then we would like these numbers to be more relaxed, the example values more relaxed or less demanding in the report. P by theta scan has a similar performance matrix. Again, we are looking at basically the magnitude within 4 to 40 hertz, that the magnitude should be higher than particular value, like 0.5 per unit per radian, and then the phase to be closer to 180 degrees, as in this case. Here is one slide which really shows why we need to keep sometimes this limits to be more relaxed. So here is transfer function from energy to theta. So instead of P by theta, it is E by theta. Energy, as you know, is integral of active power. So a flat gain in P by theta would give us this type of like a single order pole type of response, where the gain would be very high at low frequencies. So what it means is that to keep that P by theta gain to be really flat, as you go towards lower and lower frequencies, you would need more and more amount of energy response or energy storage within the device to meet that requirement. And again, which might not be possible for certain resources which do not have inherent storage inside them. So when we apply this performance matrix, we have to be mindful about to which technology we are applying, whether something with energy storage like eStatCom or battery energy storage system, or something without internal storage. And the last frequency scan test is V by I or impedance scan. So here you are seeing the impedance response of two grid forming BESS. The blue ones are response measured using vendor-specific black box PSCAD models, and the dashed lines are the response of an RL reactor or RL branch, basically resistive at low frequency and inductive at high frequency. So we are comparing the positive sequence impedance response of two BESS with that of an RL branch. And from that, we can estimate, okay, what is the amount of inductance these two BESS are providing. This inductance you can convert into the short circuit ratio or dynamic short circuit ratio, because we are not really looking at short circuit currents, but just the impedance of this resource within this particular frequency range. So performance matrix is that the impedance response should resemble that of a reactor, similar to pass-fail criteria, and also that the reactance that you estimate from this V by I or impedance scan should be smaller than a particular threshold, in this case 0.75 per unit. What it means is that this particular resource should give the short circuit ratio or dynamic short circuit ratio of more than 1.33, which is just inverse of 0.75. If the size of inductance is or reactance is even small, that means that grid forming resource is contributing higher level of grid strength to the system. So with that, I'm coming to the last part of the presentation so that we have enough time for Q&A. So this is not included in the ESIG report that we release in September. We'll work on this topic as like a subsequent item, sizing of grid forming resources using frequency scans. So how can you use these test methods and performance matrix to size grid forming resource to meet certain grid strength improvement objectives for ensuring bulk system stability? So let me show that by an example. Here is one 200 megawatt IBR inverter-based resource connected to grid in single machine infinite bus format. And this particular IBR has a characteristic that it becomes unstable whenever the grid strength or short circuit ratio is less than 3. And that we can see in this time domain simulation. When the short circuit ratio is dropped to 2.5, the plant starts oscillating, it becomes unstable, and eventually it trips. Now, we want a specific objective. We want to size a grid forming BESS at this POI to stabilize this particular 200 megawatt IBR in a grid condition with SCR of 1.5. So we selected a 150 MVA BESS model from like a black box PS card model and did its Q by V frequency scan, as you can see here in per unit by per unit. Within the frequency range of 4 to 40 hertz, its gain is actually lower, like it's pretty much flat, but it falls towards the lower end at the low frequency with gain of around 2.53. So to be conservative, we selected this particular lower gain instead of selecting a higher gain somewhere around this point. So what it means is that this 150 MVA BESS is providing dynamic short circuit ratio of around 2.5. Now, for a 200 megawatt IBR, that same 2.5 would be 1.9. So this implies that if I connect this 150 MVA BESS at the POI of that 200 megawatt IBR, the BESS would contribute the dynamic grid strength of equivalent to what a grid would contribute of SCR of 1.9. So what this should mean is that 200 megawatt IBR should remain stable if the grid's short circuit ratio is around 3 minus 1.9 or basically around 1.1. So it should remain stable to such significantly weaker grid, even though it was not without this BESS. And that is what we confirmed this with time domain simulation. We connected this BESS at the same POI and then kept reducing the grid strength. And the IBR becomes unstable only when the SCR is reduced to 1.1 and it starts oscillating. Now, there are a lot of assumptions over here. Like I'm showing you just Q by V scan. You might ask, what about P by theta scan? So this varies from IBR to IBR, whether the IBR needs grid strength support on active power or reactive power or both. And also there are some approximations because we're ignoring some coupling elements, but the matrix and the test methods based on Q by V scans and P by theta scans, they really provide a good way of quantifying grid strength from grid forming resources, which we can use to side grid forming resources for meeting particular grid strength objectives, which is just this slide where talks about that how we can size grid forming resources without models and EMT studies if we know this performance matrix. So if IBR developers guarantee stability for their IBRs for grid short circuit ratio above a particular threshold, and as a system planner, you would know what is the deficit or what is the actual short circuit ratio where you are connecting those IBRs, and then calculate the deficit of IBRs. That can be met by grid forming plants by properly procuring the Q by V and P by theta response, or basically, in other words, procuring active and reactive power response. Deepak, I would let you summarize this slide deck. I think you give nice summaries, and also because you can answer tough questions.
So the way we have structured this setup is that the core functionality that we've been exploring in this entire work is the representation of a voltage source behavior. Now, getting ahead a little bit of myself, and especially going to the second bullet point, which is about upcoming specifications like Unify specifications. The way this is all being built up is to be like a multi-fronted approach where there will be different kinds of functionality that we're going to be looking at from frequency domain to build up this overall, I think, take Nick Miller's concept like a super soldier inverter, where an inverter would have all the properties that we are looking for, right? And that's where these frequency domain scans will fit different parts of that entire setup. So we've been looking at the specific aspect of grid strength and support stability in this particular effort here. But by no means is it mentioning that every control structure, every control scheme will fall under this category. And that is where that super soldier aspect about the different types of frequency domain functions that we're building up will come out soon in the follow-up work that we're talking about. And the metrics that are here, firstly, they give an idea of whether the resource does provide the capability or not. There is some leeway in terms of defining the exact value of frequency ranges that we're looking into. There is bounds for an OEM to have a few exceptions based upon equipment limitations that are there. They also have the ability to provide insight into whether a particular resource can actually provide help or benefit in a particular location in the network or not. And then overall lead up towards a standardization effort wherein we miss a lot when we do only time domain kind of evaluations, and a frequency domain evaluation and a characterization can actually help tell much more about what a particular resource is doing on the network, be it whether we do it from a measurement-based perspective or do it as a black box simulation model perspective. It can provide much more insight. So that's pretty much summarizing, I think, what we had here.
Thank you, Deepak. And oops, I pressed the wrong button.
Thanks so much, Shahil and Deepak. There are a lot of questions. So let's see how many we can get through. The first one is, can those methods be used for validation of EMT models against measurements obtained from testing?
Yeah, we did that actually recently for a 2 MVA PV inverter. We presented a paper at PES general meeting this year using frequency scans for model validation. So yes, you can use frequency scans to validate the model.
Thank you. The next question is, could you clarify what is frequency of the impedance and transfer functions frequency plots? Is it DQ frequency? Is it absolute? What tools are used for scans?
Let me answer that question for maybe this Q by V scan. So when you look at the frequency at the x-axis, that is really the frequency of perturbation we are injecting in the input variable, which is voltage in this case. It comes in denominator. So basically, they modulate the magnitude of voltage at the POI of a grid forming resource at that particular frequency. And then we look for a response in the reactive power output at that same frequency. So it's just the frequency of perturbation in the input variable, which in Q by V scan is voltage magnitude. In P by theta scan, it's the voltage phase angle. In V by I impedance scan, it's actually positive sequence perturbation. So it's not voltage magnitude or angle, but it's more like additive perturbation. So it depends on which transfer function you are using. We haven't used DQ admittance or DQ matrix in this particular case, but it is possible to use that as well. Deepak, you want to add anything on this?
No, it's fair.
Okay.
As you said, the frequency that is being plotted there is essentially the frequency of perturbation, which is being applied. So if it's the Q versus V, then it's the magnitude of voltage being perturbed with a sinusoidal perturbation.
The next question is QV. It is operating point dependent. How to interpret this aspect?
I think that's a great question. And for that, I would like to go to a slide that I had before. So here you are seeing the Q by V scans of this one synchronous condenser, and then the color scans are from 3 different grid forming BESS from 3 different vendors. The solid lines are when these BESS are dispatched at 0 power. As you can see in the legend, maybe it's too small. The dots are when these BESS are dispatched at the full power. And we did the scans to understand, okay, how the operation point impacts the Q by V scan. And again, I have seen this in many different examples that it doesn't. Like as long as you are operating within the same control mode, the Q by V gain is going to be the same. But that again doesn't mean that you are getting the same grid strength, because for small signal stability, yes, you are getting the same grid strength. But for large signal transients, like some bigger disturbance, if you're operating the BESS at full power, and if there is a disturbance, the BESS might saturate, and its grid strength during that period will suddenly go down. This gain will go down. And that's why we have to be careful on how we use the small signal characteristics for sizing large signal response. But the gain really, we haven't seen it changing with the operation point. Deepak, you have any?
That's the idea behind using these functions. So power versus reactive power versus voltage, active power versus angle, both in this form or in the inverse form, is that it allows for a little bit of operating point independency. Now, if we use more of the impedance related functionality, then there is more of operating point dependency that comes into play when we're looking on the impedance or admittance. But the reason behind using these functions here is that the operating point independent nature of the functionality actually makes it very easy to carry out the scan. But as Shahid said, if you hit a limit, if you go into a saturation, if you have a hysteresis inside your loop, if you have a dead band in the controls, depending upon what type of resource one is operating, those elements will play a role in determining or in providing a different kind of a response. So for example, say the Q by V scan, if a resource has a dead band of, let's say, 0.05 PU in their voltage controller loop that exists, and if one is operating or carrying out the scan at 1 per unit nominal voltage, the dead band will essentially play a role where you wouldn't see a certain behavior. And if you do the same scan with the same perturbation magnitude, but rather than doing it at 1 per unit nominal voltage, if you do that scan at, say, 0.95 or 0.94 per unit voltage, which is outside the dead band, one can get a different response in the scan. So that kind of operating point dependency is actually dependent on nonlinear elements in the control, which is, it's not the aspect of the characteristic of the resource itself, but it's more about similar to a limit or a saturation element playing a role.
Yeah, and maybe one point I would like to add here is like on adding further, like why we use Q by V or P by theta scans and not something else. So one reason is it has a good correlation with voltage jump and phase jump test. So you did that if you understand time domain test, this is just looking at the same response in a different frame of reference, which gives much more clarity and flexibility in defined specifications. When I say flexibility, what I mean is the Q by V scans or P by theta scans, or for that matter, any frequency scan is independent of the grid condition. Like the time domain response would change depending on what SCR you are using, but frequency scan would stay the same if you do it properly. The second major reason for this is that we are looking for grid strength from grid forming resource. And it might be possible that some IBRs need grid strength support only for reactive power or basically voltage control. So by dissecting this two different performance metrics, active power response and reactive power response, we can have flexibility in having like higher Q by V scan gain, basically higher grid strength contribution in that axis compared to in the active power, which again, if we talk about resources which doesn't have storage, we can still leverage that. So that is another reason why not just use simple impedance, but also look at these other scans which are looking at active and reactive power response separately.
Thanks. And there was a second half of that question. What is the rationale to specify frequency region 4 to 40 hertz to decide it is GFL?
I can add my thought on this, and then Deepak can add. So it's just really about selecting a fast time scale, because we don't want to go into steady state realm where even with grid following controls, you can have droop gains and provide that primary frequency response or something similar for voltage response. We wanted to look at fast time scales. That is one reason to convert that fast time scales into 4 to 40 hertz. You can push the 4 hertz to even little lower value like 1 hertz. The second reason is most of the instabilities we see coming from big grid, they fall within this 1 to 30 hertz range, 1 to 25 or 30 hertz range. And this performance metrics are really targeting those big grid instabilities. And that is second reason why we want this behavior of voltage source behind reactor to mitigate those big grid stability issues.
Yeah, and adding on to that fast timescales perspective, it's a very crude way of, let's say, comparing or drawing a mapping between frequency domain and time domain. Saying it outright, it's very crude, right? So it shouldn't be dissected to nth detail, but a very crude approximation is that 4 hertz frequency perturbation will relate to the quarter cycle time duration of that 4 hertz is roughly going to be 60 milliseconds or 50 milliseconds. So it's roughly looking at the speed with which a voltage step change or a frequency step change would occur, or the ramp at which that would occur, and then the kind of response that we want for that kind of an event that occurs. That plays a role in determining the frequency range. And as Shahil mentioned, it can be changed around depending upon network to network.
The next one is the size of phase jump related to grid voltage behind the impedance or the voltages at POI?
In this particular report, we have used the grid voltage phase jump because I think it is very hard to have the exact phase jump at the POI, particularly if you have some impedance between the ideal voltage source and POI when you're emulating certain big grid conditions. So the phase jump is applied within this within this ideal voltage source.
Right. The next question is, given that phasor domain transient model is valid up to 40 hertz and most are not valid above 4 hertz, is it really possible to use phasor domain transient models to test the proposed grid forming criteria?
Yeah. So it's a mixed response here, right? So the idea here is that not to say that the phasor domain model can be used up to 40 hertz. It's definitely also not the case that phasor domain model is not valid above 4 hertz. In fact, there are very good phasor domain models that many OEMs have developed that are valid up to around 9 to 10 hertz. So what we do use this approach here is that to a certain extent, we can, especially if you're looking up to the bandwidth of phasor domain software, we can get an understanding of the grid forming property, but we can't get the full range. The added benefit, though, about the phasor domain approach is that it's more about looking at it from the perspective of parameterization and just ensuring good robustness of the model.
The next question is, no transformer is considered in the testing. The POI is always assumed to be an infinite bus. It has question mark behind it, but there is no question.
Yeah, I'm not sure if I understand the question, but one thing I would like to say is that when I showed that the hardware scans, if you look at the gains over here, they are like significantly higher, like 10 and more than 5. The reason is because this is a Q by V scan of unit level scan, where we only include the unit level transformer for performing the scan. So there's not significant impedance. But when we do this plant level scans, the high voltage substation transformer is also included. The cables in between them are also included. So the gains would be lower. So now depending on whether you are characterizing the performance of unit or plant, it can be the gains you will see will be different. Yep.
Thanks. And there is a next one, and I understand the report just came out. So the question is, have you had a chance to compare ESIG report with ENSO-E's report, which is on grid forming capability of power park modules? So it's a testing report that just came out from ENSO-E. I'm not sure, Shakil, Deepak, if you had a chance to.
I haven't.
Too short a timeline to turn around that kind of a comparison unless somebody does it through AI.
Yeah, maybe something for future work. The next one is, can the transfer functions be derived from ZDQ impedance? I guess you responded to that one, but Shakil, if you want to say anything else.
Yeah, if all these transfer functions are interrelated. If you're asking about relation with DQ, you can look at this paper that we have written where we have a relationship between the DQ impedance to this power domain transfer functions like Q by V, P by theta scans. So that is a relationship and you can derive one from another.
I guess probably the last one for today is, should containerized systems for on-site GFM testing become a standard or mandatory requirement, and how widely are they used in practice today?
So
it's a question which has a lot of implications associated with it. I think my personal opinion there is there should be type testing of equipment now. And I think many standards are going towards type testing of equipment, whether the type testing gets done in the lab or gets done with the perspective of putting a container on a trailer and then taking it to the actual field and then doing tests. That there are different ways of slicing and dicing that. Whether it becomes a standard or a mandatory requirement, I think that's where, if we have it as a type test for the lowest element and then have some form of a model validation kind of a test for the entire plant, similar to what, say, something like IEEE 2800 is going towards. At the moment, probably that, at least my opinion, is that serves as a feasible path for looking at both elemental level versus plant level.
Yeah, I think it is more about question of return on investment. Like you need to balance on what you're really looking for. If you do a good due diligence of unit level hardware testing within a laboratory and validate models, then maybe you don't need containerized tests at the plant level in the field. But yeah, it depends on how much effort we are putting in validating the models.
Right, thanks so much. So we are almost at the top of the hour, and I would like to wrap up. I'd like to thank Shakil and Deepak for this really nice informative webinar. And I would invite everyone to visit the link that we provided and familiarize yourself with the report. If you happen to compare it with the ENSO-E report, let us know. As I mentioned earlier, the email will go out once the video has been posted, and we will get the answers to all unanswered questions and get them posted as quickly as possible. We appreciate your engagement and we look forward to seeing you again soon, perhaps on December 3rd, next ESIG webinar, which will be on new frontiers for IBR and data center modeling requirements, practices, and experience. And the webinar will be delivered by Ryan Quint and Kasun Samarasekera from Elevate Energy Consulting. Further information on all of our webinars and events can be found at our website at www.esig.energy under events, and you are all invited to attend. Information on all G-PST webinars can also be found at www.globalpst.org. Shahil, Deepak, thanks once again for your webinar, and thank you all for your interest and for your good questions. We look forward to seeing you again in the near future. Thank you. Goodbye.
Thank you all.
Thank you all.